We spent some time ago on position time graphs and the shapes of various position time graphs. Today we want to look at a few shapes of velocity time graphs, see what they mean, see how the shapes of position time graphs compare to velocity time graphs, see what they have in common, see what is different about the position time graphs versus velocity time graphs. If we had a position time graph that took the same shape as this first graph that we see right here, in other words, its position on the y-axis, its time on the x-axis, and it's a straight line, just like the one above it is, then what would that graph represent? What would the one in blue, the position time graph, represent? Thank you for raising your hand, Kate. Kate, what would this graph represent here, d versus t? No. Yep. Yeah, well, velocity. What velocity, though? Because a velocity could mean it's staying the same velocity. It could mean it's increasing or decreasing, or it's a constant velocity. It's staying the same, right? It's not increasing. Look, the position is increasing. The position is getting bigger and bigger and bigger, but it's not getting bigger quicker as time goes on. So the velocity remains constant. It's moving, it's changing position, but it's maintaining the same velocity, constant velocity. What about the one above it, though? What about the one above it that's in black there, velocity versus time? Here you can see that it's not a constant velocity, even though it's exactly the same shape. The velocity is getting bigger. It keeps increasing, increasing, increasing. What do you know about the rate at which the velocity increases, though? The rate stays the same. The slope of the graph stays the same. So what does that tell you about the acceleration of this graph? Doesn't it? No. It's at a constant acceleration. The velocity is increasing, but the acceleration isn't. So we're going to say this one's a constant acceleration. Does that make sense, guys? If you see a straight line, it's got to be constant something if it's a straight line. It's just a matter of what it is that's constant. Okay, position versus time, it's a constant velocity. Velocity versus time, it's a constant acceleration. Okay, next one. Let's say we had a position time graph that looked like this. What does that represent? You guys can get this one, right? What's that one represent? Yep. Right, it's stopped. It's not moving. Now, the instinct sometimes when we see that one above, where we have a straight, flat, horizontal line on a velocity time graph, is to say it's not moving. Is that true? No, it is moving, isn't it? Yeah. We know it's moving because the velocity is not zero anywhere. So it's moving. So what do you know about that, though? It's a constant velocity. It's not accelerating. So on a position time graph, this one gives us constant velocity. On a velocity time graph, this one gives us constant velocity. Let's try the third one here now. This is a velocity time graph that's sloping downwards. Let's try the position time graph that's sloping downwards. Looks something like that. Straight line. What does a straight line mean? Forget about the type of graph it is right now. Straight line always tells us something is constant, right? Something is constant. What does any straight line mean here? Constant, right? Constant what? Well, it's constant velocity, but it's going downwards, so it's constant. What does it tell you? It's going on. It's a constant velocity, but it's not the same as this constant velocity. If this is constant velocity forward, this one's constant velocity backward, right? So it's not like you necessarily get your car in reverse, but it does mean that you're going in the negative direction. We'll say constant negative velocity. If the first one is going to Calgary, then the third one is going back from Calgary, back towards Okotoks. What about that? Straight line again means constant, right? Is it constant velocity here? No. It can't be, because you can see, if you look at the graph, or if you write constant velocity for this, you're not thinking. Okay, you're remembering, and you're remembering wrong. Okay, if you think about it, See, the velocity is something here. It's something smaller here. It can't be a constant velocity if the velocity is getting smaller. So what do we know about this? It's accelerating. It's decelerating. It's a negative acceleration. But since it's a straight line, it's a constant negative acceleration. In other words, it's slowing down. This one, if you remember from earlier on in Physics 20, this one, we have a line that's curving upwards. It's not a constant anything. It's an increasing velocity. Not only is the position getting bigger and bigger and bigger, but the velocity is getting bigger and bigger and bigger as well. Well, this one should represent an increasing velocity as well, right? The problem is, so does this one. This one is an acceleration, just the same as this one, but it's not a constant acceleration. It's an increasing acceleration. In other words, the velocity is increasing, but the rate at which the velocity increases. It's not only the velocity itself that's getting bigger, the rate at which it gets bigger is getting bigger. And finally, the last one. We had a position time graph here. This would mean the position is changing, but the rate at which the position changes decreases. In other words, it's slowing down. It's decelerating. It's slowing down. The last one, this one's slowing down. Look at the y-axis. Is it slowing down? What's happening to the velocity here as I start at this moment and keep going to the right for time? The velocity gets bigger, but the rate at which it gets bigger is getting smaller. So that means although it's accelerating, it's a decreasing acceleration. I think I used the analogy on Friday before the break. This one would be like you put your foot on a gas pedal just a little bit. You accelerate a little bit, right? You speed up. Then you put your foot further and further and further down on the gas pedal. And not only are you speeding up now, but you're speeding up quicker than you were before. That's the fourth diagram there. The fifth one is the exact opposite. You put your foot on the floor as far as it'll go. You accelerate at a really, really high rate of acceleration. But then as time goes by, you kind of ease off a little bit. You let your foot off the gas pedal a bit. Still on there, so you're still speeding up, but the rate at which you're speeding up is a little bit less. Not speeding up as quickly as you were before. In other words, you're accelerating, but it's a decreasing rate of acceleration. Does that make sense? I gave you two more examples on Friday, I think. Ones that I don't expect you to remember, but just to see if we can work through them here. Somebody tell me what that shape was? What does that one represent? Yeah. That one's going back in time, which of course isn't possible, right? So that's a graph that you're not going to see on a test because it's not a graph that really represents anything real, that is. Okay. But it's a good test of whether you're kind of interpreting graphs and understanding graphs or just memorizing. Okay? Because we can't memorize one that doesn't exist, right? What about this one? What's happening to the velocity there? It's getting bigger, right? What's happening to the time? I've stopped time. Is that possible? No, so neither one of these are possible, and that's why you're not going to see them. But again, they're good exercises to go through to see if we're really understanding how to read graphs. Is that good? All right, how are we going to find some different things on these velocity time graphs? How are we going to calculate some things? Like we did with those position time graphs. Well, on a position time graph, we could find the position by going up and over. On a velocity time graph, if we want to find the velocity, we're going to go up and over. So if you want to find a value that's already on the y-axis, there's no calculations. All you're going to do is go up at a certain time and over and read what that velocity is at that moment in time. So if you want to find out what the velocity is on a position time graph, you got to do a calculation. If you want to find out what it is on a velocity time graph, then you're going to just read it off the graph itself. The change in velocity, you guys can give me this one. If velocity is up and over, then change in velocity is going to be up and over twice, and then what are you going to do with them? Somebody said it? Subtract the two, right? So we get two velocities by going up and over, then subtract them. So there is a calculation involved here, but it's an easy calculation, subtracting two numbers. Calculation that a grade 2er could do. Finding the acceleration on a velocity time graph. What do you think that would be? Yep. Yeah. Just like the velocity on a position time graph, right? It's going to be the slope. And you guys remember how to do slope, right? It's rise over run, or you can say y2 minus y1 over x2 minus x1. Now, finally, the displacement. This is a tougher one. Okay, you want to find the displacement on a position time graph. It's just up and over, subtract them. It's easy. On a velocity time graph, it's harder. Pay close attention to this, and then we'll do an example where you'll see how to actually go about doing this. The displacement is the area between the line and the x-axis. So in other words, in this graph that you see up here already on the board, if you calculate that area, it would be displacement. The area of that, by the way, since it's a triangle, would be 1/2 base times height. Or the displacement would be 1/2 base times height. Okay, let's take a look at an example here. And this is the example that you have on the front of the worksheet that I gave you. Exact same thing, so you don't need to recopy it. Please do copy the solution, though. Question number 1 says, what's the velocity of the object at 4 seconds? Remember what we said to do there? If we want to find a value that already appears on the y-axis, then let's just read it off the y-axis. Let's go up and over. So at 4 seconds, we're going to go up and over. The velocity at that moment in time is 15 meters per second. The change in velocity of the entire graph. Well, we're going to take two velocities, the final and the initial. The final velocity looks to be 33 meters per second. The initial looks to be 3 meters per second. So 33 meters per second minus 3 is 30 meters per second. Yep. Now the acceleration we said was the slope. The slope is y2 minus y1 over x2 minus x1. y2, well, we might as well pick our first point and our last point. We don't have to, but that's usually the easiest. Our last point is 33. Our first point is 3. So 33 minus 3 over x2 is 10 minus x1 is 0. So it becomes 33 minus 3 over 10 minus 0, which gives me 3. And it means acceleration, so it's going to be meters per second squared. So it's accelerating, not moving at 3, it's accelerating at 3. Now finally, the displacement of the object over the entire graph. This is where we find the area. Now the problem is, we got a shape here that's a little bit odd. We have a shape that looks like this. I don't even know what you'd call that as a shape. But I know it's not a square or a rectangle or a triangle. It's a combination of a rectangle and a triangle. We're going to say this is area number 1, and this one's going to be area number 2. Area number 1 is a rectangle, so it's going to be base times height, or length times width. The base here, or the length, is 10. The height is 3. It goes from 0 to 3, so that's going to be an area of 30. Area 2 is a triangle, so we're going to say it's 1/2 base times height. The base here is 10, and the height, it goes from 3 to 33, so the height would be 30. We multiply those, it gives me 150. We add those up to get the total area now. The total area, which represents the total displacement, would be 180 meters. So as you accelerate at 3 meters per second from an initial speed of 3 to a final speed of 33, we would move a distance of 180 meters. Okay, that makes some sense? All right, let's take a look at our worksheet. Okay, that's question number 1. You guys have got all the questions on the flip side of that page. Please do those now, and we'll take a look at them when we're finished here in a few minutes, okay? Remember, don't try to necessarily memorize what you got to do for each of these things. Look at each question and think about it, okay? If you're trying to find a velocity and you've got a velocity time graph, then just read it off the y-axis. Okay, the only one that's really tricky here is the displacement. You want to find the displacement, you got to find the area. Sometimes that's 2 or 3 calculations, okay? See what we can do, and then we'll take a look at it as a class. Let's take a look at question number 1 here. This one we're asked to find the velocity at 6 seconds, the change in velocity between 0 and 9, the acceleration, and the displacement here. The velocity at 6 seconds is the easy one. It's going to be up and over, so it's going to be 5 meters per second. How many people got that? Good. The change in velocity between 0 and 9, it's final minus initial. And the final velocity is 7. The initial is 1, so it's going to be 7 minus 1 is 6 meters per second. How many people got that one? Good. The acceleration is going to be y2 minus y1 over x2 minus x1. It's a slope. y2 is 7 minus 1 over 9 minus 0. So that gives me 6 over 9, which is 0.67 meters per second squared. Who got that one? Okay, good. Finally, the displacement. This one's the tricky one here. The displacement involves finding the area, but we have 2 separate shapes here. We have a rectangle and we have a triangle. The rectangle we're going to call number 1, the triangle we'll call number 2. Area 1 is base times height. That's going to be, the base is 9, the height is 1. So we're going to get an area of 1 there. Now for the second one, it's a triangle. It's 1/2 of base times height. The base is still 9. But the height this time goes from 1 to 7, so the height is going to be 6. That's going to give me 27. We add those up, we get 28. Now, Javi over here was asking a question about the units. Good question. He says, since it's area, the units are going to be meters squared, right? How many people put meters squared for the area there? Nobody? What'd you put for the area then? Austin? Sorry? Oh, yeah. So, boy, that's pathetic when I can't even multiply 9 times 1, hey? You know what's even more pathetic? One of you said something, and the other 26 of you didn't say anything. 9 times 1 is 1. Thank you, Austin. We add those up, it gives me 36, right? Okay, let's go back to my question now that we've got my poor math skills figured out here. 36 what? Meters squared? Why isn't it meters squared? It usually is when we find area, it's meters squared, right? Why isn't it meters squared here? Yeah, you're finding area, but it's not an area of a, of a box that's meters and meters. It's the area of a funny shape that's seconds and meters per second. So if we multiply the axes there, it's actually going to be 36 seconds along the x-axis and meters per second along the y-axis. They cancel, and we're left with 36 meters. Okay, we should think about it. It should be meters, right? We're finding the displacement. Displacement is going to be in meters. So it makes sense that it should end up being meters here. Let's try the second one. I know this one gave people a little bit of trouble with the negatives here, okay? So let's make sure that we're good with this. The velocity at 6 seconds, easy, right? Up and over 4 meters per second. The change in velocity between 0 and 8. This one's a bit tougher. It's final minus initial. The final velocity at 8 seconds is 0. The initial velocity is 16 meters per second. Negative 16 meters per second. Listen, it's slowing down. We should have a negative change of velocity here, not a positive, because it's slowing down. The acceleration, that's going to be the slope. y2 minus y1 over x2 minus x1. y2 is 0 minus y1 is 16 over 8 minus 0. Gives me negative 2. And the units are going to be meters per second squared. Finally, the displacement. Think area, 1/2 base times height, 1/2 of 8 times the height of 16. It's going to give me 64. And what are the units for that? You guys know this, right? The area, which represents the displacement, is going to give me units of? Right, 64 meters. Good. Is that okay with the negatives there? Everyone, why this should be neg 16 and why this one should be negative 2 as opposed to 16 and 2? Okay, if this was a test or if this was a quiz, then in all likelihood this question A would be worth a point. Okay, B would be worth a point. If you forgot the negative, you'd lose a half a point there. Okay, C would probably be worth 2 points. If you forgot the negative, you'd lose a half a point probably. Okay, and this one's probably worth a point or 2 as well. So a quiz out of 6 or 7 points, you end up losing a full point because you forgot negatives. Okay, we don't want to do that. Next question, third one. The velocity at 12 seconds, easy enough. Up and over. 5 meters per second. The acceleration between 0 and 8. Well, it's y2 minus y1, 5 minus 0, over x2 minus x1, over 8 minus 0. 5 over 8 is 0.625, I think. The acceleration between 8 and 18. Who got this one? What's the acceleration between here and here? Dustin? Why 0? The velocity is remaining constant. Who did a calculation for that one and got 0? Nobody? Yes, you did, Liam? Okay. Who just looked at it and said, oh, it's got to be 0 because it's a flat line? Okay. Both are fine. The calculation obviously means a little bit more work, but it's just as correct. When you find the slope there, you go y2 minus y1. It's going to be 5 minus 5 over 18 minus 8, which is going to give you 0 every time. And finally, the displacement. Okay, here we have a triangle and a rectangle. This is 1, this is 2. Area 1 is 1/2 of base times height because it's triangle. 1/2 of 8 times 5, which is 20 meters. And in the area of number 2, the rectangle is going to be base times height. It's going to go from 8 to 18. The base is 10. The height is still 5. We add those up. Who got 70 meters for that? Who didn't get 70 meters? Okay, for those of you who are having a little bit of trouble, does that make sense? Get 70? Does it make sense what we're doing here now? Okay, one more. The acceleration between 0 and 25. Between 0 and 25, right, Kate? Between 0 and 25. We're going to go from here to here. Okay, that's going to be final minus initial, 80 minus 0 over 25 minus 0. 80 divided by 25 is 3.2. Between 25 and 45, well, we're going to say it's 0 minus 80 this time. Final minus initial, over 45 minus 25. Does that give me negative 80 over 20, which is going to give me negative 4. Who got those two? Who got the negative in there? Good. Okay, it's a small thing, but it's important. Okay, we want to get 100, right? We don't want to get a good mark. We want to get 100. We're okay with those? So good that we could have ourselves a quiz tomorrow? Think so? Should we review this one more time tomorrow and then have ourselves a quiz on Wednesday on this stuff? Just to make sure that we're okay. Okay, that's what we'll do. Okay, that's what we'll do. So we'll have a quiz. Mark this down now. We'll have a quiz on Wednesday. I'll remind you tomorrow as well. One more little thing that I want to do with you here, guys, and that's acceleration time graphs. We've done position time. Okay, we did those weeks ago, and then we reviewed them again today. We did velocity time today, similarities and differences. Now I want to look at only three acceleration time graphs. We won't do anything beyond recognizing the shapes, no calculations, nothing like that with these graphs. Just recognize the shapes. Okay, in the first one here, if I had a position time graph that looked like this, it would represent constant velocity. A velocity time graph, it would represent constant acceleration. This is neither of those. Here you can see that the acceleration is increasing. So it's like put your foot on the gas pedal a little bit, put your foot further and further and further down on the gas pedal. So not only are you speeding up, the rate at which you speed up increases. So it's an increasing. Acceleration. Next one. If I had a position time graph that looked like that, what would it mean? Easiest question in the world. Position's not changing. What does that mean? You're stopped, right? The object is stopped. If I had a velocity time graph that looked like this, we would know that the velocity is what? Is constant. It's not changing. If we have an acceleration time graph, is it moving? Yes, it's not stopped. Is it traveling at a constant velocity? No, it's accelerating. Look, the acceleration is not zero. It's accelerating. It's not traveling at a constant velocity. So what do we know about this? What's not changing? The acceleration. So we're going to say here there's a constant acceleration. The third one is the one that people mess up on. If we had a position time graph like this, it means a constant negative velocity. You're coming from Calgary to Okotoks, not from Okotoks to Calgary. If we have a velocity time graph, it means you're moving forward, you're going towards Calgary, but your velocity is getting smaller, so you're slowing down. It's a deceleration. If we have an acceleration time graph that looks like this, what does that mean? Lots of people will say it's accelerating backwards. Is that right? Accelerating in the negative direction? Not at all. Look at each of these values of acceleration. They're all positive. It's accelerating forward. So what do you know about this? The analogy with the gas pedal again. Put your foot on the gas pedal, put it to the floor. You accelerate at a really, really high rate right here. As you ease off the accelerator, you're still speeding up, but your acceleration is decreasing. So you're still speeding up, still going faster and faster and faster and faster, but the rate at which you speed up is decreasing. Right? Take your foot off the gas pedal. Okay, not all the way off, because then you slow down, right? But just ease it off. You still speed up, but not as quickly as you were before. That's what's happening here. This is not a constant acceleration, not an increasing acceleration, but rather a decreasing acceleration. Still positive velocity, still a positive acceleration, but a decreasing rate of acceleration. You guys okay there?